Hello everyone, we will work on section 14.7 today, and please be patient with me and with this course, of course, because this section is on the longer side. Okay, it's maximum minimum value. Okay, I will start with some review from Calculus 1. And you will see how we carry those important ideas in this Calc 3. Now, in Calc 1, we say that a point x equals to a of a function y equals to fx is a critical point if the derivative of that function at x equals to a is 0. Sometimes we say we write it as, I think we write it this way. We write f prime a equals to 0, right? Now, or so either this one or this one, or the first derivative of the function at x equals to a is undefined, while a is in the domain of f. So there are two ways to have a critical points. The first one is when the first derivative equals to 0. Okay, let's say the graph looks like this, right? Then at this point, x equals to a, the first derivative equals to 0, which basically means we have the horizontal tangent line, right? Okay, or another case when we have a minimum. We have horizontal tangent line also. We have the case where the first derivative is 0 at a, and therefore it is a critical point, but it is not local maximum, not local minimum. Okay, so the first derivative equals to 0 may be one of the requirement, but that's not all we need. Okay, we need something else. Okay, we need something else. Now, for the second case where we call it undefined is when the first derivative is undefined, but it is in the domain, still in the domain of the functions. So for example, for this case here, x equals to a, where the tangent line is actually a vertical tangent line, but the function that x equals to a is still in the domain of the function. If you remember, this is the classic case for example, y equals to square root of x. You know, the first derivative is 1 over 2 square root of x. Then from here, you see that the domain of the function is 0 to infinity, including 0, right? But the domain of the first derivative does not include 0 anymore, right? So this is undefined at x equals to 0, right? That's a classic example. Okay. Of course, another one is when we have a cusp, something looks like this. You know, basically, we call that undefined because we end up with a vertical tangent line. Okay. Now, we say it's critical points because those are the points, those are the axes where the value of a function may be the maximum or the minimum. Okay, so for example, in the last two cases here, you can see that this is that coordinate there is at least the local maximum, right? And this is the local minimum. Now, in this case here, you see that x equals to a is a critical point, but it is not local maximum, not local minimum. Okay, x equals to a is a critical point, but further observation tells us that it is not local maximum, local minimum. Okay, now I hope from there we notice something, that critical points only provide us the candidates for local maximum, local minimum, but it is not sufficient condition. It's a necessary condition, but it's not sufficient. Okay, now then we can say more. Then what is local max, local min? A critical point is a local max or local min if, maybe let's talk about the maximum first. Local max if fa is greater or equals to fx for x near a. So what I meant is this, like if you pick any x in surrounding of a, you will see that the y value of those x's is actually less than fa, right? So you see that this is the maximum in this interval. Okay, that's on the top, right? Likewise here, if you choose any number surrounding a, then the value of when x equals to a give us the maximum value, the highest. Okay. Now, in other words, later on in this section, one way for us to get the local maximum, local minimum on the domain that is more than one dimensional is to find the critical points first and then see how the value of at that critical points compare to the values of the coordinates near that critical point. Now it will be local minimum if fa is less than or equals to fx for x near a. Okay, the more precise mathematical terminology we say for x in the neighborhood of a. Okay, now going further in calculus 1, we can trace if x equals to a is local max or minimum by two methods. The first method, the one that I think you commonly use, is by using the second derivative test. Right, so we basically see that the second derivative at a, if that's positive, it means it's concave up. And therefore, x equals to a is local minimum. And the second derivative of a is negative, which means it's concave down. And x equals to a is local maximum. Provided the first derivative at a equals to 0, right? Okay. But this first derivative test has some drawbacks, some weaknesses. The first one is what happens if the second derivative does not exist, right? Okay. What happens if the second derivative does not exist? Or what happens if the second derivative is 0? Then we cannot say anything, right? Okay. So we have a second way, which is actually more traditional way, behavior of f prime x around x equals to a. Now, let me give you an example. This is something I did not do in the past in my Calc 3 class, but I will do today. I want you to be aware that my lecture notes that I do here basically coming from the lecture notes I already have since 2007. Yes, 2007, not 2017. I have these notes from 2007. Of course, in between, I update it again and again and again. So what I give you here may feel quite heavy, like not only for today, but all my lectures, because those are combinations of so many years of notes that I put together, then it becomes a lot more comprehensive. Okay, let's review a little bit from your Calc 1, and I hope you remember about this. Okay, so suppose we have, for example, in example 0a, call that 0a, we have, let's say we have fx equals to x squared minus 4. X squared minus 4x. Now we know it is a parabola, opens up with x-intercept at 0, 0 and at 4, 0. Just factor it, then you will see that, right? So we know that we have local minimum, okay? But how did we use calculus 1 to find that it is local minimum at 2, and how do we show, without graphing, how do we show using calculus 1 that it is actually a minimum? So we do the first derivative, and we set it equals to 0, and we have x equals to 2, right? So then we know that x equals to 2 is a critical point. So at this point, we know x equals to 2 is a critical point. But we don't know yet if it is the local maximum, local minimum, or neither. Okay, so what we will do is we do the second derivative, which gives us 2, and then check at that point f second derivative at 2, that's still a 2, which is positive, which means it's concave up, right? Okay, but if it is concave up, but at that point the tangent line is horizontal, then from there we see that at this point we have x equals 2 is is part of the graph, that is concave up. Now then from there we can conclude, So x equals 2 is a local minimum, right? Okay, I purposely use an easy example here so that you can imagine what the graph look like. Okay, but the nature of the spirit of these methods, basically we try to find the local maximum or local minimum without graphing them. Okay, now the second example. The second example, what happens if the first derivative equals to 0? Let's say if we have fx equals to x to the fourth. Now you see that the first derivative is 4x cubed, which when we set that to be 0, we get x cubed equals to 0, and therefore x equals to 0. So we know x equals to 0 is a critical point, right? Unfortunately, when we do the second derivative, we get 12x squared. So the second derivative at 0 is 0, but 0 doesn't tell us if it is concave up or concave down. Okay, notice I say it doesn't tell us, doesn't mean it is not. Okay, it's just saying that this second derivative test is inconclusive. Okay, we cannot say anything from there, so we need to go through another method. Okay, so at this point we know that x equals 0 is a critical, but the second derivative test fails to second derivative test does not provide concavity. Concavity. Even though if you think about it, x to the 4, as you have learned supposedly in your pre-calculus class, that's a power function, right? Which means it is a polynomial with degree of 4. So it behaves, the shape is like this. And we know that x equals to 0 is where we get the local minimum. Okay, but what I'm trying to say is, like in this case, the second derivative test does not provide us conclusion. It's inconclusive. So what can we do? What can we do? Then, because the second derivative test is inconclusive, then what do we do? Then we see the behavior of that first derivative of that function near the critical points. So we go to plan B. Our plan B is, okay, do the sign graph. When x equals to 0, what happened to the f prime x? When x equals to 0, the f prime x is 0, right? What happened with f prime f prime at 1? When x equals to 1, f prime 1 is positive, which means the slope is increased, the function is increasing, right? And when we check f prime at -1, it's negative. In other words, when we look at the function itself only, okay, the function is decreasing to the left of 0 and it is increasing to the right of 0. Now that tells us from here, that tells us that x equals to 0 is a local minimum again. Okay. Yeah, try to compare what I did here in example 0b with example 0c. When we have fx equals to x cubed. Now you will see the graph of x cubed. I hope you do know this. The graph of x cubed looks like this. Okay, the first derivative is 0 at 0. The second derivative is 0 also at 0. So the second derivative test is inconclusive. So you need to do the sign graph for the first derivative. Okay, when you do the sign graph for the first derivative, you will see, let me work it out. So the second derivative will be 6x, right? Now where we have f double prime 0 is 0, it's inconclusive. But then, because the second derivative test is inconclusive, we take a look on the sign graph for f prime x. So when x equals to 0, the first derivative is 0. When x is positive, the first derivative is positive. When x is to the left of 0, the first derivative also positive. It means the function is increasing and then becomes horizontal and then increasing. From there we know this is x equals to 0 is not a local max nor a local mean. Okay. Now, the third example, we anticipate the case where the first derivative is undefined. Okay, let me do it here. The classic example is the one I showed you earlier for square root of x, right? Fx equals to square root of x, and then the first derivative is 1 over 2 square root of x. Okay, now we take a look at the domain. The domain is from 0 to infinity, but the domain of the first derivative does not include 0, right? From there, we see that at x equals to 0. Now take a look. How do we determine that? X equals to 0 originally in the domain of the function, but suddenly it is not in the domain of the first derivative, right? Now from there, we see that x equals to 0 now is a critical point because the first derivative is undefined there, yet it is in the domain of the original function. Okay, now because it is not in the domain of the original function, it is impossible for us to do the second derivative test. Okay, in other words, I just try to remind you that the second derivative test you use in your calculus 1 is not without flaw. Okay, there are weaknesses. Okay, what happens if the second derivative test gives you 0? Then we need to use another method, right? What happens if you cannot even do the second derivative test? Like the critical point comes from the first derivative that gives us undefined, but it is in the domain of the original function. So what can we do? Well, we can't even do second derivative test. But we can find the second derivative, Thomas. Yes, you can. You can find the second derivative, but x equals to 0 is not defined there, right? It's not even defined in the first derivative, right? It's not in the domain of the first derivative. What makes you think that it suddenly becomes in the domain of the second derivative, right? Okay, so what do? Then we take a look on the behavior of the first derivative around 0, around that critical points, right? It is undefined here. It's undefined here, but to the right-hand side, the first derivative is positive, which means the function is increasing there, nothing here, nothing to the left of that, right? Which means at x equals to 0, it must be the minimum. So x equals to 0 is local minimum. Okay, I hope this is a good review from your Calc 1, right? Okay, I did mention earlier, I think I mentioned that many times, that simply because it is a critical point does not imply it is where we have local maximum minimum. Okay, now so we come up with, remind ourselves with this theorem from Calc 1. Note, we also know from Calc 1 that if fx has a local max or minimum at x equals to a, and the first derivative of a exists, then the only way the first derivative of a at a exists is when the first derivative equals to 0. Okay, remember that first derivative equals to 0 is a required condition, one of the required condition for local maximum or local minimum, but that's not sufficient. Okay, another condition is when the first derivative is undefined but is in the domain. Okay, in other words, I want to go backward from this note here. That's what you usually see in Calc 1, but the consequence is this: if the first derivative at a is not equals to 0, okay, but maybe I write it another way. Equals to a constant, equals to a number which is not equals to 0, then f x does not have critical point at x equals to a. Okay, it's not even critical point, so we don't talk about local max, local min. We will bring this discussion now to calculus 3. Associate with fxy. Okay, now I go to the realm of calculus 3. So first note, first one, of an f of xy has a local max or local mean at a comma b. Notice that this is in the domain of the function if fxy is less than equals to fab for xy near ab. So think about this, like let's say this is the domain, right? And this is coordinate AB. We say this is the maximum. This is the maximum if the surrounding area gives you a value less than the value at AB. Okay? So if you choose an XY near AB, okay, then f of that xy must be less than or equal to the value at AB. Then we know that at AB you have the local maximum. If you can randomly choose that fxy near, so one of the keyword is like near that AB. Okay. Now that's for the first one. That's basically definition, right? Now if fxy has a local max at AB, then the value at AB is a local max value. Now I want to distinguish the position, the location of local max, which is the coordinate AB, and the value at that position. The value of that position is FAB. Okay, just to illustrate the terminologies, if we have x squared plus y squared, you know what it looks like, right? This is equals to r squared, right? So it's actually a paraboloid, right? It's a paraboloid, okay? And local mean at 0, 0. But the local minimum value is C at 0, 0, which is 0. Okay? Now that's the first note. The second note. If fxy has a local max or minimum at AB, and the partial respect to x, the partial respect to y, both exist. So if the partial derivative exists, and we know it is local maximum or local minimum, then it must be because the first derivative, the partial derivative respect to x equals to partial derivative respect to y equals to 0. Okay, now this second note here actually parallel to this note here. If you have local maximum or minimum at a certain point, and the first derivative exists, then it must be because the first derivative is equal to 0 there. Okay? Now, what happened with the local max, local minimum? For two-dimensional domain, if the partial derivative with respect to x and y are both exist, then it must be because the partial derivative equals to 0. Now, you can imagine this guy here at this point, you know, the partial derivative respect to x and partial derivative respect to y are both horizontal, right? Okay, in fact, think about the tangent plane. The tangent plane must be horizontal. Okay, so maybe I write it as a note. The tangent plane is horizontal. Maybe to be more precise, parallel to xy plane is parallel to xy plane. Okay. Now, the third note. So you see how I slowly build the case from what we have in Calc 1. Okay, the first note here is basically the prediction of local maximum, local minimum, right? Now, the second note basically saying that if you know it's local maximum, minimum, and the first derivative exists, the partial derivative both exist, then it must be because the first partial derivative is equals to 0. Now, let's reverse the situation. If the partial derivative respect to x at AB is equals to 0, and the first partial derivative with respect to y at AB also equals to 0, then AB is a critical point. Remember, we only call it critical points because we don't know yet if it is local maximum, local minimum. But if any local maximum, minimum happen, then it must happen at this point, provided the partial derivative exists. Okay, now don't forget that we actually have the case where the first derivative does not exist, yet it is critical point. Okay, so the one we are dealing with right now is when we have first partial derivative equals to 0. Okay, or you will see later on either the first derivative not exists, or the partial derivative respect to x or respect to y not exists at x at AB, but AB is in the domain of the function. Okay, so we are now dealing with this case. We are dealing with this case. Okay, we are dealing with that case. Now, let's see a little example for now. Okay, I hope I don't wait until it gets too complicated, then we start doing example, right? Suppose I have let fx y equals to x squared plus y squared minus 2x plus 6y. So we do the first partial derivative with respect to x, we will get 2x minus 2. If we set that equals to 0, we get x equals to 1. Now, the partial respect to y will be 2y plus 6. If I set that equals to 0, then I get y equals to negative 3. Consequently, 1 comma negative 3 is a critical point, right? But at this point, we don't know yet if it is local maximum or local minimum or neither. Okay, I think at this point, we actually can tell if you happen to be able to visualize the situation, right? We know that this fxy here, if I complete the square, it will give me x squared minus 2x plus 1 minus 1 plus y squared plus 6y plus 9 minus 9. I plus minus 1 plus minus 9 because I complete the square, but at the same time I need to compensate for that addition. So I get x minus 1 squared plus y plus 3 squared minus 10. You see, this is actually a paraboloid. Paraboloid with vertex at 1 comma negative 3, right? In fact, the vertex, to be more precise, the vertex is 1 comma negative 3 comma negative 10, right? But in the domain where it hits the minimum, it's like minimum at 1 comma negative 3, and the minimum value is negative 10. But going back to our calculus 3 method, at this point we can only say it's a critical point. We cannot tell yet if that critical point is local maximum, local minimum, or something else. Okay, from here then we get to the next one. the second derivative test. Second derivative test. So, suppose the function fxy is continuous in the surrounding of AB, where the derivative respect to x and respect to y at AB equals to 0. And therefore, AB is a critical point, right? Now, define, we create a new function, DAB. This D actually, we can call this discriminant, and you will see it has some pattern of discriminant that we learned in quadratic formula. In quadratic formula, our discriminant is b squared minus 4ac, right? Okay, but we call that discriminant because that tells us if the quadratic solutions, the solution of the quadratic equation has two real solutions, only one real solutions, or two complex solutions. Okay, so the idea behind the background why we call that D here, basically because we want to say that's our discriminant. Okay, even though this is the discriminant not for solving a quadratic equation, but to see if a critical number point is a local maximum, local minimum, or neither. Okay, now this discriminant will be defined as f sub xx at AB times f sub yy at AB minus the square of f sub xy at AB. Now, and if the discriminant at AB is positive and the second derivative at x at AB also positive, then local minimum at AB. If the discriminant is positive, yet the second partial derivative with respect to x and x is negative, then local maximum at AB. Okay, if the discriminant is 0, then inconclusive. We cannot say if it is local maximum nor local minimum. Now, what happens if the discriminant is negative? Then we say it's a saddle point at AB. Okay, now you may wonder what is saddle point. We have this case many times. something looks like this. So it is a saddle point because if you go travel along this path here, that is actually local max. But if you travel along this path, that's actually local mean. We call that saddle because it looks like a saddle when you ride a horse. Okay. So through one path, that's the local maximum. Through another path, that's the local minimum. Now, so let's try using this second derivative test for our example number 1. Okay. Oh, you know what? Before I go on, this is important. Note that discriminant AB may also be written as f sub xx AB, f sub xy AB, f sub yx AB, f sub yy AB in determinant form. So that D that I called discriminant earlier may also see as the determinant of 2 by 2 matrix. Okay, where if you think about it, this part here, f sub xy, and then this is f sub yx. In general, they are not the same, but if they exist, then they will exist the same. They will be the same, right? Okay. Now, if you remember how to compute the 2 by 2 determinant, A, B, C, D, the determinant of that is AB minus BC. Okay. However, if the mixed partial derivative are both continuous, then they must be equal. That's from the Clairaut's theorem. Okay, that's from the Clairaut's theorem. Now, this determinant here is also called Hessian. From somebody with last name Hess. I don't know the history behind it. I just said it here to try to respect that person. Okay, but you will see this notation or this determinant a lot when you go to partial differential equations, at least at the beginning. Okay, now let's take a look at the next example where we will apply example 2. We will apply the first derivative test and the second derivative test, and I hope that will explains how tedious it can be. Okay, so let fx y equals to 2x cubed plus xy squared plus 5x squared plus y squared. We don't know what the graph look like, and no, we are not trying to look at the graph and then determine, because you may see what it looks like, but you still cannot tell what's the local maximum, local minimum, right? Don't forget that the graph may be misleading, right? Okay, now you will see the first step we do is to find critical points. It is by doing the partial derivative with respect to x and partial derivative with respect to y. I will set this equals to 0, and the secondary, the partial derivative with respect to y will give us 2xy plus 2y. I will set this equals to 0. Now you see I have a system of two equations with two variables, but they are not linear, so we don't expect this to be easy, right? Okay. Call this equation 1, call this equation 2, I will work with equation 2, seems to be easier. 2xy plus 2y. When I set that equals to 0, I get y times 2x plus, 2y times x plus 1. So either y equals to 0 or x equals to -1, right? Now then, use this plug that into the first equation. Okay, when I plug that into first equation for y equals to 0, what happened? For y equals to 0 in equation 1, then I will get 6x squared plus 10x equals to 0. I factor the 2x out. So I get either x equals to 0 or x equals to -5/3, right? From here, then, we see that x equals to 0, y equals to 0, and x equals to -5/3, comma, y equals to 0 are critical points. Okay, but for x equals to -1, I get 6 times -1 squared plus y squared plus 10 times -1 equals to 0. That's 6 plus y squared minus 10 equals to 0. I get y equals to 4. Y squared equals to 4, so y equals to plus minus 2. So when x equals to -1 and y equals to 2, x equals to -1, y is -2. Those are critical points. Okay, so this is the critical point phase. We look for critical points. Now then, the second step, we do second derivative tests. Okay, let's do the partial derivative respect to x again. So f sub x is that. When you do another derivative with respect to x, we get 12x plus 10. F sub y of xy will be 2x plus 2. And f sub xy at xy will be 2y. Right? Notice that we will get the same thing for f sub yx. You know, it's polynomial, so the mixed partial derivative will always exist and therefore continuous and therefore equal by Clairaut's theorem. Okay, now so what is our determinant? Determinant at xy, or you can also call that discriminant at xy, will be 12x plus 10 times 2x plus 2 minus 2y being squared. Now, don't multiply this. Don't multiply this. Just leave it like that, because our purpose actually just to compute the determinant at those critical points. Right? At 0, 0, and we just care about the positive or negative. Okay, so I will write it this way. This will be positive times positive. Oh, you know what? No, not safe. Let me write the number then. So that will be 10 times 2 minus 0 squared. That's 20. Okay, notice that it is positive, yet the second derivative respect to the second partial derivative with respect to x and x is positive also. Consequently, at 0, 0, that will be local maximum. I'm sorry, local minimum. Okay, now let's plug in when x equals to negative 5/3. When x equals to negative 5/3, what will that be? 12 times negative 5/3 times plus 10 times 2 times negative 5/3 plus 2 minus the y is 0 squared. That is negative, I don't know, negative 10 times, that's negative 10 times, what is that? Negative 10 over 3, 6, that's negative 4 over 3. I just need to know that's negative. So this is still positive, right? But because the first derivative, I'm sorry, the second derivative with respect to x and x is negative, then we know at negative 5/3 comma 0, that's local max. Okay, at negative 1 comma 2, so this will be when x equals to negative 1, that will be negative 2 times 0 minus 4 squared, right, which is negative. That's negative 16. And once the determinant is negative, we know that's a saddle point. Okay. I think that's the same with this, negative 4 squared, that's still negative 16. So that's at negative 1 comma negative 2 is also a saddle point. Okay, so take a look. I'm actually working on these and apply to these coordinates. Okay, and I try to purposely write it in a way that I can see my f sub xx, my f sub yy, so that I can visually easily to visualize the conclusion. Okay, now that's for this second derivative test. Next one. In fact, let me, instead of like doing it right now, let me stop here for a while and give you the suggested homework. Let me call this 14.7a. 14.7a, and your suggested homework will be suggested homework for 14.7 part A will be from number 5 to number 19. Okay. Now then I will go on with the second part of this section. Let me call that 14.7b. I hope by breaking up this way, then you can see the breakdown, why we do what I do. Okay. The second part is still, this is still 14.7b. This is maximum minimum value. On in, or maybe I should say in a closed bounded domain. Okay, what is the association of this, the parallel of this in calculus 1? In calc 1, we have this theorem. If the function f(x) is continuous on a closed interval ab, so let's say you have a function, right, and you have interval a and b, continuous and close. Okay, then we will have f(x) attains its maximum and minimum values at a critical point in AB. Notice that now I changed it into open interval, which means does not include the endpoints, or at an endpoint that is x equals to A or x equals to B. Okay, so take a look on this graph here. Like in this interval A to B, the curve looks like this, right? The curve looks like this. You can see that the absolute minimum is absolute maximum. You see that the absolute minimum is at x equals to A, and the absolute maximum is somewhere in between where the first derivative equals to 0. Okay, that's what we learned from calculus 1. Now, in general, what I'm about to say right now is called extreme value theorem. I think that they call it in calculus 1, extreme value theorem. It hits the local the absolute maximum or absolute minimum either at the critical point or at the endpoints. Okay, now what is our extreme value theorem for calculus 3? In higher, as I remember, it's been a long time I don't deal with higher math, but as I remember, maybe called closed bounded theorem. I forgot though, closed bounded theorem. For sure, we may call that closed bounded theorem, which basically says the following. Okay, if the function of xy is continuous on a closed and bounded set in the domain, then f(xy) attains its absolute maximum its absolute maximum or minimum. Let me rewrite it. Its absolute max and minimum at x naught y naught, which is in the domain, and this x naught y naught is either a critical number or critical point, or on the boundary. Okay, I think I need to first explain what is a closed and what is a bounded set. Now, a closed set, let me write it properly. Note, region D is bounded if it does not go to infinity. Okay, for example, on the two xy planes, something looks like this. That's closed and bounded also. Okay, now the following is not bounded if we talk about the first quadrant. The first quadrant, you know, it's not bounded because it goes infinitely far, right? Okay, I can say, even though I don't like this definition, it's not totally true. It is bounded if, for now, a very easy version, if the area is finite. Okay, if the area is finite, even though I have to say that we may have the area of certain region to be finite, yet it is not bounded. Okay, bounded basically, you know what, I think another way to say that it is bounded is that you can enclose that. Okay, you can enclose that like this. Let's say our domain actually, our D is actually something. This is our D. Okay, and then you can enclose that with a curve, a closed curve. Okay, that's bounded. Now, second, a region D is closed if it includes its boundary. Now let's take a look. Let's take a look on an example of closed region. But I need you to be imagine this a little bit. Imagine the following. Let's say I call this D to be the set of xy, where we have square root of 4 minus x squared minus y squared. Okay, so you see that this D here must have the following condition. This guy must be at least 0, right? Okay, in other words, x squared plus y squared is at most 4. That's basically a circle with radius 2 with the interior, right? We usually call this a disk, right? Okay, now this is closed and bounded. This is closed and bounded. Okay, why we call that bounded? Well, because I can enclose that, right? Easily enclose that. Oh, okay, then it's bounded. Okay, this is closed and bounded. Now, can we find a region D which is bounded but not closed? Oh, easily. Find the oh, you know what? I can kind of like write it incorrectly. Now, this is suppose you have this function f(x,y) square root of 4 minus x squared minus y squared. Then the domain is that, right? Okay. Now imagine if I change that function, call that function gxy as 1 over square root of 4 minus x squared minus y squared. You see the domain, therefore, all coordinates where 4 minus x squared minus y squared has to be strictly positive and cannot be 0. Right? Let me emphasize that. It cannot be 0. Right? Okay, and you will see, gada boom, you will see x squared plus y squared is strictly less than 4, which means the domain is the region inside that circle, not including the boundaries. Is it close? No, it's not close, because the boundary is not included in that region. Is it bounded? It is bounded, because I can easily enclose that. Right? It's bounded. It doesn't escape to infinity. The domain is not super big, right? Okay. But because it doesn't include its boundary, then it is not closed. Okay. In fact, the idea of bounded and closed have been introduced implicitly even in calculus 1. You basically have to apply this extreme value theorem in calculus 1 into a closed interval and bound it. Okay, hold on, Thomas. Hold on. So in your examples here, you show us both of them bounded, one of them closed, one of them not closed. Can you show us an example of a region that is closed but not bounded? The whole planes, the whole xy plane, that's closed because it includes its boundary, which is infinity, right? But it is not bounded. Can you show us a region that is bounded but not bounded but also not closed? Easy. The first quadrant. The first quadrant is not bounded, but it is not closed either. Okay, why? Because on the first quadrant, if you look at the first quadrant only, now first quadrant is defined to be where x and y are both positive, right? So we don't include the x-axis and the y-axis, right? Okay, so this is not bounded and not closed. Okay, now this is bounded and closed. This is bounded but not closed. Okay. Now, if you want not bounded but closed, well, just include the the x-axis and y-axis. Then suddenly it is not bounded but closed. Okay. Yeah. Anyway, that's the little explanation about what is bounded and what is closed. Okay. Now, what this theorem says that if you apply this function on a closed and bounded set D, then the function must have its absolute maximum and minimum at either the critical points or on the boundary. Okay, now let's take a break first, and then when we come back, we will apply what we have here. Now you will see what we do from here is actually just application. Now the thing is, the application is quite far-reaching. It's quite difficult, actually, if I can say, quite tedious. I think I will give you some examples, 3 examples maybe, and that will basically take our whole period. So there's a chance that I won't even be able to touch 14.8, but we worry about that later. I rather explain this very well. Okay, let's take our break first. Right now it's approximately 6 o'clock. We come back at 6:10. Okay, I will go over 3 questions, and I hope through these 3 questions you can see the difficulty, the complexity of this problem. Okay, it's not with the math, it's more about the strategy though. Okay, let's see the first example for this case. Let fxy equals to xy minus x minus 3y on a triangular region with vertices 0, 0, 0, 4, 5, 0. So we are actually looking at this situation here. So our vertices are 0, 0, 5, 0, and 0, 4. Okay, that's our situation. So we are dealing with this domain, this bounded region. I hope you follow me in graphing though. Okay, so everything on this boundary and inside of that. Okay, now let's see the plan first. So let me write the plan here. The plan will be, first we want to find the critical numbers or critical points in the interior of D. Okay, now second, we go along the boundaries of D's, usually denoted by dou D. So that notation beside as the partial differential notation, that's actually to show the boundary of region D. Go along the boundary of D to find critical points along the boundaries. Okay, now for each of these critical points, for each of critical points from number 1 and number 2, we compute the values. We find the values. And then conclude the maximum, minimum. Absolute, max, or minimum. Notice that we are not dealing with the local maximum, local minimum. Okay. Find the absolute maximum, the absolute maximum, and minimum. let's see how we will execute this plan. Okay, but this is the plan. Let me make it a bit smaller. Okay, now let's see our step one, critical points on in the interior. In the interior of the domain D, or in the triangle. Okay, we take that fx, we do the partial respect to x, we get y minus 1, partial respect to y, we get x minus 3. We set them equals to 0. This is easy, so we get 3, 1, right, is a critical point, is a critical point in the interior of D. Okay, let's find the value. So F31 will be 3 times 1 minus 3 minus 3 times 1. That's negative 3. Okay. Second, how about the critical value on or along the boundary, on the boundary of that D? The thing is, the boundary consists of 3 portions. Okay, let's call this the first path. Let's call this gamma 1, gamma 2, gamma 3. Okay, you can also call that L1, L2, L3, up to you. Just call it and make sense. Do not use the variable that we usually use though. For example, do not use x1, x2, x3. It doesn't make sense, right? Okay, you get confused even more. Okay, so let's go along gamma 1. That is the line segment from 0, 0 to 5, 0. Right? Now, so that's on x-axis from x equals to 0 to x equals to 5. But the y equals to 0, right? Okay. Now, because the y is equals to 0, then the function f x0 now becomes a single variable f0, fx only. Okay, that will be what? When y equals to 0, then I get negative x. Compare it to the original function. Yeah, when you plug in y equals to 0, what happened? You get negative x only, right? Okay, now we know this is decreasing. Okay, so because it is strictly decreasing along that x equals to 0 to x equals to 5, then the maximum minimum will only happen at the endpoints, right? Remember on the boundaries we are talking about, that boundaries consist of this part here, which is the interior of that interval, and the endpoints. Okay? But since we know the function is decreasing, then the maximum minimum will happen at the endpoints, which is at 0, 0 or 5, 0. Okay, so we don't have the critical numbers, critical points, none, right? It is strictly decreasing. The endpoints are 0, 0 and 5, 0. Okay, so let's see what is f0, 0. f0, 0 is 0. And then f5, 0 will be -5. Okay, that's along gamma 1. Along gamma 2, that's on y-axis, from y equals to 0 to y equals to 4, of course, because it's y-axis, then x equals to 0, right? When we plug in x equals to 0 on the original function, we get -3y. So f0y equals to -3y. It is still decreasing, but on that interval from 0 to 4 decreasing, then the critical points is known, but endpoints are 0, 0, which we already have earlier, right? And 0, 4. Okay, so f0, 0, we know that's 0. f0, 4 is -12. By the way, at this point, we already know we have a new local minimum. You see, if we compare this guy and this guy, this guy and this guy, right? You see the maximum is 0 for now. The minimum is -12 for now. Okay, that's why we don't need to do the second derivative test unless you need to know if each of those critical points are local maximum, local minimum. But the question is about absolute maximum minimum, right? So if it is just local maximum minimum, we don't worry about that. Okay, we just try to find the critical numbers in the interior, critical numbers on the boundaries, and the vertices of these boundaries. Okay, now that's along gamma 2. How about along gamma 3? Now this is terrible because it is on the segment, line segment, from 5, 0 to 0, 4. Or you can also do from 0, 4 to 5, 0, up to you. Okay, now from here, let's parameterize that. I will say that gamma 3 is managed by RT, where the T will be from 5 to 0. So I will control my T from 0 to 1, right? Okay. So x, you will see the x when x equals to 0. I mean, when t equals to 0, the x is 5. When t equals to 1, when t equals to 1, the x is 0. Now, but my t needs to go from 0 to 4. So let's call this 4t. Now, in case you wonder, Thomas, how do you get that? Think this way. Just so we go back again, right? How do you get that? Think this way. Factor. Okay. So what is the direction factor? The direction factor v is 0 minus 5, right? 4 minus 0. The terminal points to initial points. Remember, that's a line segment, right? So the direction factor is -5, 4. Okay. The initial point is 5, 0. Okay. So we parameterize that by 5, 0 plus t times -5, 4, right? That's how we get that 5 minus 5t, and then we have 4t here. But because it's line segment, it's not a full line, right? Then we limit how the t can move from 0 to 1. Of course, this is not the only way to do this though. Okay, like before, I said many times, to reparameterize a curve, we have so many different ways, but this is one way. Now then we will plug this f now into the coordinate, this path here into the coordinate. Okay, so what's that again? Xy minus x minus 3y. X y minus x minus 3y. Okay, let me write the shadow. X y minus x minus 3y. Okay, this becomes 20t minus 20t squared minus 5 plus 5t minus 12t, which will be negative 20t squared. 25 minus 12 is plus 13t minus 5. Right? Now notice that this is an upside down parabola, right? Okay, now we do the first derivative of this respect to t then. That will give me negative t 40t plus 13. When I set that equals to 0, I get t equals to 13 over 40. When t equals to 13 over 40, what is RT? RT will be 5 minus 5 times 13 over 40, comma, 4 times 13 over 40. I know it's ugly. Bear with me. That is 5 minus 13 over 8. And this is 13 over 10. 40 minus 13 is 27. That's 27 over 8 and 13 over 10. Okay, now that's the critical points, right? Okay, so what happened is the critical points is 27 over 8, 13 over 10, and then the endpoints are 0, 0, which we already know the value, and 0, 4. I'm sorry, the endpoints is 5, 0 and 0, 4. Both we know the values already. Okay, so values at 5, 0 is what? I know I computed earlier. Negative 5. The value at 0, 4, we computed earlier. What's that? Negative 12. Okay, and the value at 27 over 8, 13 over 10. Let me just plug that in here for the corresponding t. That's negative 20. What is the t again? 13 over 40 squared plus 13 times 13 over 40 minus 5. Let's see. What is this? That's 13 squared over 40 times 2 negative plus 13 squared over 40 plus, I'm sorry, minus, I do the LCD. So you see I do this without calculator. So this is 200 over 40. So this will be 169, negative 169 over 80 plus, let me do LCD 80 right away. 169 times 2 is 338 minus 400 over 80. What is that? 62. That's negative 229 over 80. That's the value. Okay. Let me use my calculator just for sake of simplicity when I compute that later on. What happened with my calculator? Where's my calculator? Here. Calculator. 229 divided by 80 equals to negative 8.2, negative 2.8625. I hope I don't miscompute it though. Yeah, check my computation here. Okay, but according to my number, I get negative 2.86 what 25. Okay. So at this point, we can already conclude that the critical points and endpoints are 0, 0, 0, 4, 5, 0, and then 3, 1. Make sure this 3, 1 is in this though. So 3, 1, I think is 3, 1 is here. So it is still in the triangle, right? In the region. 3, 1, and then what else? 27 over 8, 13 over 10. Now this should be on the here, somewhere here. Okay, somewhere there on the path. Okay, and then the value, this is 0. What is 0 for? Negative 12, as I remember. 5, 0 is negative 3. Is it right? 5, 0. Oh, I'm sorry, negative 5. At 3, 1 is what? At 3, 1 is negative 3. Then at that coordinate is, oh, hold on. Is it positive or negative? Let me plug that in. It's negative, huh? So here is negative 2.8625. Why do I get something else here? Did I compute my stuff properly? Give me a second. I wonder if my coordinate here is even correct. I did my computation correctly. Let me make sure, okay? Let me make sure. So when I do the derivative with respect to the combined like terms, 20, 25 minus 12, that's 13. So yeah, I'm correct so far. It's strange, it's different from my notes. Oh, no. I'm good. My bad. I'm good. So from here, I'm sorry. So from here we see absolute maximum equals to 0 at 0, 0. That's absolute maximum. Absolute minimum is negative 12 at 0, 4. Okay. I don't know if I make any miscomputations, but the technique is basically like that. Okay. I did not use calculator for this, so please check my work. Okay. Next example. Example 2. Let fxy equals to x squared plus 2y squared minus x for D be the all the coordinates where x squared plus y squared less than equals to 4. So this is a disk with radius 2. Okay, this is a disk with radius 2. Approximately like this. Okay. Now, so let's first find part 1, the critical points in the interior of D. By the way, this is notation for the interior of D. What I do first, I do the first derivative with respect to x, the first partial derivative with respect to x. I get 2x minus 1. I will set it equals to 0. I get the x equals to 1/2. And partial respect to y, I get 4y, only set it equals to 0, so I get y equals to 0. It's negative 231 over 80. Negative 281 over 80. Thank you. So when you divide, what is that? Negative 3 something? Oh, negative 3 something. Huh? Oh, 281 or 231, by the way. I'm sorry. 231, my bad. Yeah, 231. Thank you. So 231 and negative 2.8875. Yeah, thank you very much. Okay, 8875. Let me correct that here. Thank you, though. Oh, good thing that we still have the same absolute maximum minimum for example 1, huh? Okay, let me come back here for example 2. So from here we see that the critical points in the interior is 1/2, 0, right? And the value at 1/2, 0 will be 1/4 plus 0 minus 1/2. That's negative 1/4, negative 0.25. Okay, actually, if you happen to see this as, you see, this is actually, if I complete the square, this is x squared minus x plus 2y squared. This is x squared minus x plus 1/4 plus 2y squared minus 1/4, right? To compensate that, I get this is x minus 1/2 squared plus 2y squared minus 1/4. So from here we see this negative 1/4 is actually absolute minimum. Like even if the domain is not restricted here, that is the vertex, right? That's the vertex. So you will see that this is actually the absolute minimum. Okay, but let's say for now we don't see it because in general, most of the case, we don't know what the graph look like, right? But if we do, of course, that would be very helpful. Now, I think our issue is how about the absolute maximum though. So let's see the critical points and on the boundaries. Okay, so we are dealing with that the curve, let's call that gamma, to be x squared plus y squared equals to 4. How would you play with this? Remember, this is your function, right? Okay. Of course, one way is you solve for y equals something, right? But don't forget, when you do square root, you should apply the positive, negative. So if you do that technique, that you need to be aware that you have two paths, the positive path and the negative paths. Okay, if you do it that way. Okay, now sometimes it becomes easier, sometimes it's not. The one I think I will do here is as follows. I will parameterize this using RT. The radius, you see that's a circle with radius 2, right? So I will use 2 cosine t, 2 sine t, where the t will be moving from 0 to 2 pi. Remember, in chapter 12, I told you how to parameterize, I think it's chapter 13 also, how to parameterize a curve, right? That is important. We need that very much here. So the value of the function at RT, now I replace the x by 2 cosine t, the y by 2 sine t, okay? So we end up with 4 cosine squared t plus 8 sine squared t minus 2 cosine t. Okay, notice that we have 4 sine squared t here that I can combine with this. I get 4 plus 4 sine squared t minus 2 cosine t. I hope you see that. You break it up this way. Actually, you will see you don't need to do that though, because what we really need is the derivative, right? Respect to t, right? So that will be 8 sine t minus a plus 2, I'm sorry, 8 sine t cosine t. 8 sine t cosine t minus plus 2 sine t, right? And then I set it equals to 0. Okay, I can factor the 2 sine t. So I get 4 cosine t plus 1, that is equals to 0. Either 2 sine t equals to 0 or 4 cosine t equals to -1. And then you solve for t. Using that t, you plug that in to find the coordinates. But it turns out that I can actually do it quite easy here. So notice that 2 sine t is actually your y, right? So this is your y equals to 0. Okay, so when y equals to 0, then your x will be plus minus 2, right? Okay, your y is 2 sine t. Okay, but when your y equals to 0, you plug that in, you get x to be plus minus 2. Okay, now likewise, 4 cosine t equals to -1 means cosine 2 cosine t is -1/2. Okay, that is your x equals to -1/2. You see what I mean? So when your x equals to -1/2, you plug that in, x squared plus y squared equals to 4. So 1/4 plus y squared equals to 16/4. So y squared equals to 15/4. Y is plus minus square root of 15/2. Okay, so our critical points on the boundaries are 2, 0, -2, 0, right? And then -1/2 radical 15/2, -1/2 negative radical 15/2. Of course, don't forget the endpoints of this parameterization, which is 2, 0, right? Because when we parameterize that, we parameterize when t equals to 0 to t equals to 2 pi, right? So the endpoints is t equals to 0 and t equals to 2 pi, which both of them give us 2, 0. Okay, this happens to be endpoints also. Okay, now let's see what's the value. So the value at 2, 0 is what's the function again? X, y equals to what? Let me see, where's that? X squared plus 2y squared minus x. So this will be 2 squared plus 0 minus 2. That's 2. At negative 2, that's negative 2 squared plus 0 minus negative 2. What's that? 4 plus 2, that's 6. F at negative 1/2 square root of 15 over 2, that will be negative 1/2 squared. Plus 2 times square root of 15 over 2 squared minus negative 1/2. That will be 1/4 plus 15 over 2. That's 15 over 2 plus 1/2. That's 16 over 2. That's 8. That's 8.25. And then for negative 1/2, negative square root of 15 over 2, that's the same function, we just replace this, right? That will be 8.25 as well. Now then from here we see that in conclusion, absolute maximum is 8.25 at negative 1/2 square root of 15 over 2 negative 1/2 negative square root of 15 over 2. Okay, absolute minimum is what's that again? Negative 1/4, as I remember, yeah, negative 1/4, negative 0.25 at 1/2 comma 0. Is it 1/2 comma 0? Yeah, 1/2 comma 0. Okay, let's try to visualize this. Let me go to my GeoGebra. Give me a second. And then we have z equals to x squared plus 2y squared minus x. So that's what it looks like. Notice that the tip, if we zoom in, notice that the bottom is not, oh, I'm sorry, this should be x here. Now you see that the bottom is actually slightly below xy plane, right? Slightly below xy plane. Okay? Yeah, slightly below xy plane. Now, another equation, I have x squared plus y squared equals to 4. I don't like. Let me change the color here. Now, I wonder if you can see the intersection though. So, inside this circle here, this, the minimum still, this one, you see the minimum still there, right? This is still the minimum. However, the maximum is happening at the boundaries. I wonder if you can visualize the boundaries. Let me screenshot this and then put it to our notes. Okay, so on this boundary here, this is the boundary. On this boundary here, no, not dark enough. Let me use a black color. On this boundary here, on the circle, right at the circle. Right at that circle, yeah, right at that circle, you see that maximum here and then also here, right? This happens at these two coordinates on the boundaries, like on the circle. Yet the minimum happens in the interior. Okay. So if I can add more, the minimum, absolute minimum is here, abs minimum, and the ones, two of those here is absolute minimum, maximum. Now notice that we get the result without graphing them. So the challenge is actually, can you solve this problem without graphing them? Okay, can we solve this problem without graphing them? How long is this question? You see from this to here, not that long, I know, but the steps actually quite difficult, huh? Okay, I still have approximately only 10 minutes left. Let me try to do the last example. Example 3, and I may not be able to finish this, but I try my best. Let fx equals to x cubed minus 3x minus y cubed plus 12y. On D, the region, a quadrilateral region, the quadrilateral region, quadrilateral basically means a four-sided two-dimensional. With vertices 0, 0. No 0, 0. I'm sorry. I thought we have 0, 0. I wish. Negative 2, 3. 2, 3. 2, 2. And then negative 2, negative 2. Let's try to picture that. Negative 2, 3. Negative 2, 3 will be here. 2, 3 will be approximately here. 2, 2 is here. And then negative 2, negative 2 is here. So we are talking about this. The region bounded by, sorry, that's not what I want. Well, anyway, delete. And last one. Yeah, approximately like this, okay? So we are talking about this region here. Okay, let's do the critical numbers, critical points on the interior. Critical points in the interior of region D, where I do the partial respect to x, I get 3x squared minus 3. The thing is, like, this is the power of 3 in 3 dimensions, so I don't know what the graph look like, to be honest with you. Okay, but if I set this equals to 0, I will get x squared equals to 1, so x equals to plus minus 1. Okay, now partial derivative with respect to y will give me negative 3y squared plus 12. When I set that equals to 0, I get y squared equals to 4, so y equals to plus minus 2. So the critical points will be 1, 2, negative 1, 2, 1, negative 2, negative 1, negative 2, right? Okay. Notice, however, 1 comma negative 2 is not in the domain, in the D, not in the D, not in D. So we just need to observe what happened at 1, 2, at negative 1, 2, at negative 1, negative 2. Okay? That will give me 1 cube minus 3 times 1 minus 2 cube plus 12, I'm sorry, plus what? Yeah, 12 times 2. That will be 1 minus 3 minus 8 plus 24. What's that? 25 minus 11, that's 14. Is it right? And then I wonder where's my note for this. I don't have the notes. I think I lose one page. Well, anyway, negative 1. So negative 1 cube minus 3 times negative 1 minus 2 cube plus 12 times 2. That's negative 1 plus 3 minus 8 plus 24. What is that? 18? Minus 9. Oh, 15 plus 3. Yeah, that's 18. Now add negative 1, negative 2. I get negative 1 plus 6 plus 8 minus 24. What's that? 14, negative 10, negative 11. Whew. Okay, if I plot those coordinates, 1, comma 2 is here. This is 1, comma 2, negative 1, comma 2, and negative 1, comma negative 2 is here. It happens to be on the boundary. Okay, now those are the respective value. Now we see the critical points and endpoints, of course, on the boundary of D. The thing is, I need to parameterize this though. Let's call this let's start with this. This is gamma 1, this is gamma 2, this is gamma 3, and this is gamma 4. Okay, so gamma 1, where the y equals to 2, I'm sorry, the x equals to 2, x equals to 2, but the y moves from 2 to 3. Right? Okay, just replace the function right away then. So the function at 2 comma y, that will be 2 cubed minus 3 times 2 minus y cubed plus 12y. Okay, that's negative y cubed plus 12y plus 2. Okay, now then we do the partial of this function respect to we can be very because it is a function of y only, right, for this. So the derivative of this function 2 comma y respect to y will be negative 3y squared plus 12. When I set that equals to 0, I get y equals to plus minus 2. Y squared equals to 4, so y equals to plus minus 2. So the critical points are 2 comma 2 and 2 comma negative 2. But 2 comma negative 2 is not in the domain, not in D. And 2 comma 2 happens to be the endpoints also. So f2 equals to negative 2 cubed plus 12 times 2 plus 2. What's that? Negative 8 plus 26. That's positive 18. I think we have that value up there, no? No, we have that here, 18 also, huh? So at this point here, that's 18. At 1 comma 2, that's 14. At negative 1 comma 2, that's also 18. And this is negative 11. Okay. At 2, 2, that's 18. F 2 comma 3, that will be negative 2 cubed plus, no, sorry, not negative 2 cubed, negative 3 cubed plus 12 times 3 plus 2. That's negative 27 plus 36 plus 2. That's 9, that's 11. So at 2 comma 3, notice how I put it here. That's at this point, that's 11. Okay, now along gamma 2, that's when the y equals to 3, as I remember. Right? The y equals to 3, but the x is from negative 2 to 2. So fx at y equals 3 will be, what is my equation again? That's x cubed minus 3x minus 3 cubed plus 12 times 3. That's x cubed minus 3x minus 27 plus 36 plus 9, huh? So the derivative of that function of x only respect to x will be 3x squared minus 3. Set it equals to 0, we get x equals to plus minus 1. Okay, so the critical points will be 1 comma 3, negative 1 comma 3, and the endpoints are 2 comma 3 and then negative 2 comma 3. Now compute the values for all of this. Okay, I have only 1 minute left, so I will just do it fast. 1 3 f negative 1 3 f 2 3 f negative 2 3. At 2 3, I think we already computed. That's 11, as I remember. 2 comma 3, right? That's 11. But we have 2 extra new critical points along the boundaries here, right? So we get those. Yeah, you compute that, and then you go along lambda 3, and after that you will go along lambda 4. Okay, you collect the values for all the critical points and endpoints, and then you can see which is the absolute maximum and which is the absolute minimum. Let me ask you to continue with this though. Okay, and then on Wednesday when we come back, I will continue on this also. Okay, that's for today.